Alright, welcome to our discussion on graphing and analyzing functions. First, let's just review the graphing steps that we are going to do. It might not be the same in every book, but these are just a few steps to help you get all the relevant information. First step, I like to just see if I can identify the function to be a specific type of function. And maybe I'll find a Y-intercept. By identifying the function as a polynomial or a rational function, I'm able to just predict certain steps are going to be easier than others, certain areas I need to watch out for in the analysis, just a little warm-up step to get me into what this function is about, what I see, what I think. Even if you conclude, no, I have no idea, I don't know what to expect, it's still a good thing to do first. Step 2 is our first main step, where we will look at asymptotic behavior, where we are looking, are there any asymptotes? What is the long-term behavior of the function, and so on. Step 3, oh, that's an ugly little bubble there. Step 3 is where we look at increasing or decreasing behavior, where we are going to see where's the function going up, where is it going down. And then step 4, we will look at what we call concavity. How does the graph bend? Does it bend up? Does it bend down? And where does it change? And lastly, we will use all that information to make the graph of the function. So let's start with a simple type of function, namely a polynomial, and the one I want to look at is in my problem book 9.5, number 5. So there we have our function. I'll call it f of x, but you can call it y, you can call it whatever you want. Negative 2x cubed plus 3x squared plus 12x plus 2. This is going to be our polynomial. So first, we identify it's a polynomial, and with that comes some properties that I won't have any asymptotes. I don't expect any, let's call them strange things to happen. It's defined everywhere, and I can find a Y-intercept as y equal to 2 when I plug in x equal to 0. The only thing I'm left with is this 2. So I also want to make a page where I am slowly going to put information in as I follow these steps. And I'll refer back to this as we go. So we'll have our basic layout here, x and y, and we found our y-intercept to be 2. So I'll put that in over here. Let's call that a 2. Alright. Next is our main step, and because I identified as a polynomial, I know that there isn't going to be much to do in this asymptotic behavior step. In fact, you might feel that there is pretty much nothing to do. But we can say things like, if x approaches infinity, then what does my function do? For that, because it's a polynomial, I look at the leading term. Long term, the function is going to behave like its leading term. And because x gets really big positive, x cubed gets really big positive, negative 2 times x cubed will therefore get really big negative. I like to say it like that. And when x approaches negative infinity, I still look at the behavior of the leading term. That tells me how the function is going to behave long term. Now x is really big negative, so x cubed is going to be a really big negative. Another negative in front will make it very big and positive. So I can indicate that to remind myself that after all the ups and downs are done, the graph is going to go down on the right and up on the left. So as I'm completing these steps, more and more information will get put in the graph. And this is just a rough sketch of all the information that I can clean up later. So because of the polynomial, there's not much to do in step number 2. So we move on to the next one, which is our increasing, decreasing behavior. And for that, we are going to look at the derivative. So the derivative properties involved here are simple properties, sum difference property, constant times a function, and our main power rule, giving us negative 6x squared plus 6x plus 12. So that is now our function that we're analyzing to say something about our original function. So I want to clean this up and factor it in the case of a polynomial. So what I could do is take out a negative 6x to make it even easier. Then I have a negative x and a negative 2. And then I can factor that as 2 brackets. Now your factoring skill might be different. So we don't want to make it too complicated. We can always FOIL this out and see, do I get the original back? It's going to have to be factors of 2. And my larger one will get positive. FOIL it out, I get my x squared from the first ones. Outside ones an x, inside ones a negative 2, giving me negative x. And the last ones give me negative 2. So that is good. Then I'll do it on the side here. We are checking 2 things in general. We're checking when is my derivative equal to 0 and when is my derivative undefined. Now in the case of a polynomial, the second one is going to be a never. No values of x will make this function undefined, but I do get a couple when x are certain values, in this case a negative 1 and a 2, that will make the derivative 0. So these are my potential critical points at this stage. Then I like to make a little table to see how do these factors affect the eventual sign of my derivative. So we're going to mark off all these potential critical points, negative 1 and 2. So I'm calling them critical numbers. And I'm going to list on the left here all the pieces, all the factors that go in making my derivative. Together, by way of multiplication, they will give me the first derivative. And I've broken up my x-axis into these pieces, these 3 intervals. Now, negative 6 is always going to contribute a negative number. X minus 2 is 0 when x is 2. And because it is being multiplied in my derivative, it will make the derivative 0 as well. X plus 1 is 0 when x is negative 1, makes the whole derivative 0 as well. X minus 2 on this left interval is going to be negative, another negative, and then a positive for all these x values. Now, it's a familiar looking expression that you might get used to, or you can plug in some representative numbers here, maybe a negative 2, maybe in between will be a 0, and in between an easy number is a 3, and whatever it does for that x value, it'll do for the whole interval. X plus 1 is going to go from negative to positive. Now I have 3 negatives. For any of these x values, it'll be 3 negatives multiplied together to give me a negative value for the derivative. In the middle section, 2 negatives will make a positive, and in the last section, 1 negative will make a negative. So I can draw my slope lines to illustrate this further. I'm going to have a negative slope, and then a horizontal slope for my tangent line, and then a positive slope, showing that little cup shape that is going to happen in the graph. For the next one, as I pass through x equal to 0, I'm going to get a positive slope, 0, negative slope, showing that crest that is going to happen in my graph. The last thing I might want to do is to list the critical points. Now, critical points, I have to have an actual point on my graph. My function has to be defined at these x values, but they certainly are for both. My function is defined. I just need to find the corresponding x values. Alright, so when x is negative 1, we want to find the corresponding y value. And for that, of course, we look at the original function. When you plug that in on your calculator or do it in your head, you get negative 2 times negative 1 cubed plus 3 times negative 1 squared plus 12 times negative 1 plus 2, and you should get negative 5. Oops, that almost looks like an 8. It's a 5. Then, when we plug in x equal to 2, so sorry, this is negative 5. That's our first critical point, because it comes out of my list here that I'm checking, and there's a point on the graph. The function's defined at the x value. Then, when x is negative, or not negative 2, when x is 2, we'll plug that in into your calculator or do it in your head, whatever works for you. Negative 2 times 2 cubed plus 3 times 2 squared plus 12 times 2 plus another 2, and we get 22. So our next y value here is 22, giving us our second critical point. We can then wrap this up with a sentence saying f is increasing on the interval negative 1 to 2, and f is decreasing on negative infinity to negative 1, as well as, I'll squeeze it in here, 2 to infinity. So if we want to put that in on our graph, we want, so increasing on negative 1 to 2. Let's first put the critical points in. Critical points, negative 1, 5. So I'm going to zoom this in just to make the shape easier to draw. So negative 1, negative 5. Let's put that over here. And at that point, which is this one, I'm making a little cup. So I'll remind myself of that. Then at 2 and 22, I'll abuse the scale just for convenience of the shape here. 22. I have my little crest happening there. It's increasing in the middle section, which makes sense because I have to get through my Y-intercept. And then it's decreasing as I come to that and decreasing past that. So the shape is starting to form very nicely. Let's see if I have enough space here. I do. For step 4, concavity, where we are going to look at the second derivative, which means we take the whatever form of the first derivative you want. And I'll pick this first one to easily take the derivative. So I'm going to have for my second derivative, it's going to be negative 12x and then it's going to be plus 6. So there's my second derivative. Then we do our check. Second derivative equal to 0 when? Second derivative undefined when? Well, undefined never because it's a polynomial. But it is going to be equal to 0 if I factor this out a little bit. Maybe I want to take out a negative 6, let's say. And then I'll have 2x minus 1. So when I multiply it in, I get the original back. So I see then that the function is going to be 0 when x equals 1/2. So that is my potential inflection point. Then I like to make a little table to see how the pieces interact. The only number that I'm going to mark off is 1/2, and I'm listing everything on the left. Together, they make my second derivative. So, I have my x-axis, my x values split up into 2 intervals. Negative 6 is always negative. 2x minus 1 is going to be 0, we said, when x is 1/2. And because it's all multiplication, it makes the second derivative 0. Use representative numbers or however you want, but 2x minus 1 is going to go from negative to positive. Now, because it's multiplication, 2 negatives will make a positive, 1 negative will make a negative. And my function, my original, my graph is going to bend up in some way and down on the next section. What are, if any, my inflection points? Well, for the inflection points, I have 3 criteria. It has to come out of this list up here. It has to be a point on the graph. On my original, because my original is a polynomial, it's defined everywhere, so I do get a y value, and the concavity changes. That is another requirement to be an inflection point. So I just have to find the corresponding y value, and I have my inflection point. So let's go up here to see what the y value is when x is 1/2. So I have negative 2 times 1/2 cubed. Then I have plus 3 times 1/2 squared. I'm going slowly so that if you need to, you can follow along. Not everyone is skilled in the calculator in the same way. Plus 12 times 1/2 plus 2. And I get 8.5. Now we can mix the decimals here. You can go here and say this is 0.5 and then y is 8.5. You can mix it up. You can do whatever makes you more comfortable. Then we'll sum it up by saying f is concave up on the interval negative infinity to 1/2, or 0.5. F is concave down on, running out of space, 1/2 to infinity. So we have this point 1/2 and 8.5. So 1/2, let's put it over here. 8.5, let's put it over there maybe. And again, I am abusing the scale for convenient shape. So I'm bending up and I'm bending down as I go past that inflection point. Now we have a lot of rough things on this graph over here. Let's clean it up with our final graph and have a graph that's nice and neat with no real regard to the scale. I'm interested in the beginning especially to focus on the shape and let the points sit where they are, and I'll indicate them as I need to. So I have my point here, -1, -5. That's my critical point. I have my Y-intercept of 2. I have an 8.5. That was my inflection point. Put that over, not over there. I have to be a little bit closer. 1/2. Let's say that point's over there. Then at 2, let's put that up here. I think that was a 22. And that'll sit at x equal to 2. And that should be good. So let's do the left first here. We start horizontally. It's actually hard to draw on this tablet. And then I will go to infinity. Then we start horizontally, bending up. It's a little wonky here, I know. Bending up through to the inflection point where it changes to bending down. Looks a little straight there. It's a very slight bend, and then I'm going through that top critical point down to infinity in some direction. I don't know. Whoopsie, got away from me there a little bit. Let's try and be a little wider. And just go. Whoop, that is too wobbly. It's hard on my tablet. I draw, but I can't see my hand. So it's hard to get the angle just right. But we get the idea. As smooth as you can make it. It doesn't have to be perfect. You can always look at online graphing tools to graph it perfectly. By hand, it's always going to be a little wonky. So that is our first type of function, a polynomial, going through all the steps from start to finish. Alright, next up we will look at a rational function. The one I want to look at is number 16. So let's see, what is 16? I'll call it f of x. X over x squared minus 4. So we see that it is a rational function. Polynomial over polynomial. And with that, I probably expect to have some asymptotes. Some x values where the function might not be defined. So step 2 will have a little bit more to it. I can, however, still find the x-intercept as when x is equal to 0, y is equal to 0 as well. So we can start putting some stuff on our graph to see how it eventually evolves and the shape becomes more obvious. Right now I don't have much. I have a y-intercept. So, next up, asymptotic behavior. where I want to see, are there any asymptotes? What are they? How does the graph behave? And so on. Well, for that, I'm looking at my function, and to see it more clearly, I might want to factor the denominator, difference of two squares, x plus 2, x minus 2. And then I can see that there are vertical asymptotes, not x, not y, but x equal to 2, x equal to negative 2. That is where the function is going to be undefined in the rational function case. That means vertical asymptotes. So I have these two dotted lines indicating the vertical asymptotes at 2 and at negative 2. Now, at this stage, you might feel, I need to know what happens as the graph gets closer to these x values. You could, but because we know we're doing the full graphing steps, when we get to step 3, it's going to be clear what the behavior is. So right now, as I'm getting close to this vertical asymptote, the graph is going to go up or down. I don't want to spend any effort figuring out which way it's going to go when I don't really need to, because in step 3 it's going to come out very easily. So it's okay at this stage to not really know exactly, but I could make a table for the function to figure it out. Next up, horizontal asymptotes. Are there any horizontal asymptotes? Well, because it is a rational function, I know that the long-term behavior is determined by the ratio of the leading terms, which in this case, it's going to behave like 1 over x. Because the bottom has a higher degree polynomial, it will shrink down to 0. So my horizontal asymptote is the line y equal to 0. Now again, that is sitting right on the x-axis. I don't really care to figure out which way it approaches the horizontal asymptote. Step 3 is going to point that out very easily. So this is all I'm going to do in step 2. Now in step 3, I'm looking at increasing and decreasing behavior, where I need to find the derivative. So I'll look at this first version of the function and use the quotient rule. Quotient rule says bottom one squared, which is x squared minus 4, square that, and then the derivative of the top, let's do it like this, we can see them both, times the bottom minus the top times the derivative of the bottom. Let's extend my line. That is the quotient rule. Now I definitely want to clean this up. So let's clean up the numerator. Let's not skip too many steps. I have x squared minus 4 minus 2x squared over x squared minus 4 squared. Let's clean up the numerator a little more. I have, let's write it like this first. Let's just see it. Negative x squared minus 4. We can take out a negative 1, and then it becomes x squared plus 4 over x squared minus 4, everything squared. Now be careful, one has a plus, one has a minus. The sum of squares cannot be factored, but the difference can be factored. So I'll clean that up a little further by factoring it so that we can see how to get our critical points out. Difference of two squares, still x minus 2, but now everyone there gets a square. So this is going to be my version of the derivative that I may want to look at. So take care and make sure you can follow all these steps. Let's see how much space we have. We have lots of space. So I can say here my derivative is 0 and my derivative is undefined for certain x values. That is where my critical points will come from. Can my derivative function ever be 0? Well, in the case of having a numerator and a denominator, I look at the numerator. Can that ever equal 0? Well, you might want to write down the equation if you're not sure, and it's going to be where x squared plus 4 equals 0. But that means x squared is equal to negative 4, which can't happen. So, whether you write this down or not, whoopsie, there are no x values, making the function 0. But there are some where the function is undefined. That is going to be when x is negative 2 as well as 2. So those are our potential critical points coming out. Whether or not they're actual critical points is kind of irrelevant. I list them on my function all the same. On my table, I mean, sorry. So we have a lot more in our table, but still just broken up into 2 pieces. On the left here, I will indicate all the pieces, negative 1, x squared plus 4, which I cannot factor. Maybe you can list every single piece. Let's maybe list these 2. Let's list them all. The simpler each piece, the easier it is. But you can definitely condense this table if you want to. This is the very detailed version. Adapt the table to your needs as you want. Negative 1 is always going to contribute a little negative. X squared plus 4 we've established up here can never be 0. It's always going to be positive. X plus 2 is 0 when x is negative 2. Same for this x plus 2. It is in the denominator, so it makes the function undefined, the derivative function. It's going to go from negative to positive, negative to positive. X minus 2 is 0 when x is 2. And it's also in the denominator, makes the derivative function undefined. It's also going to go negative to positive over its 0. So, all these by way of multiplication and division. How many negatives do I have for the first section? 1, 2, 3, 4, 5. So the answer will be negative. 1, 2, 3. So the answer will be negative. 1. So the answer will be negative. So if I look at my slope lines, it is going to be a downslope, and then bad things happen, and another downslope. Downslope, bad things happen, downslope, in the sense that there are no points. When I look at my original function, I can't plug in x equal to 2 or negative 2. So there are no y values. The function is undefined. So we'll say up here, there are no critical points. They are potentially critical because they come out of this list, out of these 2 checks, but they're not points to be called critical points. I can, however, sum it up by saying f is, it's all decreasing in this case. On the intervals, I have to break it up at negative 2 and 2 because it's not in the domain of the function. It's not defined there, so I can't include them. I can't just write negative infinity to infinity. That would not be right at all, because that implies that the function is defined everywhere, and it's not. I have to say negative infinity to negative 2, as well as negative 2 to 2, as well as 2 to infinity. I have to split them up like that. It does, however, give me my information. I have no critical points, which makes sense on the graph. I'm jumping over these asymptotes. Now have a look at these arrows. On the left section, going up to negative 2, I have everything's decreasing everywhere. So it cannot be this, because that implies an increasing trend. So I'll make my, how do I erase? Let me just find the eraser here. I think it's this button, yes. Can't be that one. And it can't be that one. I have to go down. I have to also go down from negative 2 to 2. Can't be this one, because that would be up. And it can't be that one, because that would be an increasing trend. So I have to go down throughout. Same over here. Cannot be this one. That would be going up. Can't be that one, because that would be going up in the trend, and it has to be this way, in some way. So now for this simple rational function, the bend in the graph is something you can probably guess, but let's complete step 4 to be sure. Checking my space. Ooh, can we fit that in? I am not going to try. Oopsie, sorry. We're over here. I'll just quickly make a new page. And then zoom it a little bit. So here's going to be where we're at. Our first derivative that we want to use will probably be this guy. So next we want to do step 4, which is concavity, where I have to find the second derivative. And I'm going to look at the most convenient version of the first derivative. I just took the negative back in, so up here. And it's going to be the quotient rule, and it's going to be a little messy, but it is the way it is for this type of function. So I have my bottom one squared. So let's start with that. So it's x squared minus 4. It was squared. Now another squared means to the power of 4. Then it's going to be the derivative of the top, which is negative 2x, times the bottom, which is this bracket squared, minus the top, negative x squared minus 4, times the derivative of the bottom, which is going to require a little chain rule, 2 times the bracket to the power of 1, times the derivative of the inside function, and there is our quotient rule done. Now it's a matter of cleaning up the top here. I'm going to leave the first term the way it is, and just see what I can do with the second one. I'm going to take this minus into that first bracket and put the 2 and 2x together. So then it becomes x squared plus 4, and the other x squared minus 4 is still there, over x squared minus 4 to the 4. Now see how these guys are all the same. So I can take, in the top, one of them out as a common factor, be left with negative 2x times the other bracket, because there were 2, plus 4x. This bracket is still there, This bracket is now out. And still, the denominator is the same. Now I can cancel one of them with one of those, leaving 3. And simplify the top, multiplying the negative 2x in for negative 2x cubed, and plus 8x, this one in, negative 2x cubed, this one in, positive 8x. And 4x in gives me 4x cubed, and plus 16x. Same denominator. Nothing changes there right now. Then I have 2x cubed terms, which I'll put together as 2x cubed. And these two together will be 24x. Same denominator. It's very easy to make a little mistake here. Please be very careful. Now I can take out a 2x and be left with x squared plus 12, which is a plus, so it's not going to factor. I can, however, factor the bottom at this stage because I am done. There are 3 of each of these. And there is my second derivative. Now, let's look at our 2 checks. Second derivative is 0 when? Well, either one of these in the numerator is 0. One of them is an x, so that can be 0. But this is x squared plus 12, and that can never equal to 0. Otherwise, x squared is equal to negative 12, which is impossible. So only 1. And the second derivative is undefined when the denominator is 0, and I get my 2 and negative 2 again. So I have 3 potential inflection points. Now I'm going to make my table, and it's split up according to negative 2, 0, and 2. And I list all the pieces on the left. I'll keep 2x together, x squared plus 12. And this time I'm going to put these guys together, but feel free to split them up. Together, one way or another, it gives me my second derivative. So I have now 4 intervals, 4 pieces to consider. 2x is 0 when x is 0. It is in the numerator, makes the whole thing 0. It's going to go negative to positive. X squared plus 12 is never 0. It's always positive. X plus 2 is 0 when x is negative 2. It is in the denominator, makes the second derivative function undefined. It's going to go negative to positive. Please make sure that you know why. X minus 2 is 0 when x is 2. In the denominator, makes the second derivative function undefined. It's also going to go negative, oops, that was a negative, to positive. So now, in the first section I have 3 negatives, then I have 2 negatives, then I have 1 negative, then I have no negatives. So I'm bending down, up, down, up. Let's write them down here. F is concave up on negative 2 to 0, which one should be included? Not -2, because my original function is not happy with -2, but it is happy with 0. And it's also concave up from 2 to infinity. And again, my original function not defined at 2. F is concave down on -infinity to -2, not including 2, functions not defined. 0 to 2, not including 2, but I am including 0, the function is defined there. Which of these guys are critical points? Not critical, I'm sorry, inflection points. Well, I have to be a point. So that rules out 2 and -2. So my only contender is 0. Do I have a y value when x is 0? Yes, I do. It is 0. So this point is an inflection point, 0, 0. Just happens to be the y-intercept. So I'm bending down, then I'm bending up, down, up. And we have enough to fill in to make our graph. I'm just going to make a better looking one over here, but you can of course update it as you want to. So I have my 2 vertical asymptotes, 2 and -2. I have my y-intercept, and I know for the left section it's going to be in this bottom left corner over here, like so. Trying to not be too wobbly. I'll do the right one next, up here, top right. It's going to be straightforward, a familiar shape that I've seen in rational functions already. Now, let's just have a look at what happens. I have to come towards 0 from the top, bending down, and changing to bending up. The temptation here is to maybe go horizontal, like so. It's like an x cubed type shape. But have a look at the first derivative. The first derivative is not 0 at x equal to 0. In fact, if I plug it in here at 0, what am I going to get? First derivative at 0. It's going to be -4 over -4 squared. It's not 0. It's -4 actually. So that means I have to come through this 0 point correctly. So I'm gonna come at it at an angle. Little wobbly, I know, that's my pen. Not horizontal through there. So a couple of things to have a look at. It's a fairly familiar function, quotient rule, but the quotient rule can get quite messy, so it's important to go slow and steady to get my eventual graph. Alright, the next one we want to look at is an exponential function, and I want to look at number 22. E to the negative x squared. Let's call the function f e to the negative x squared. So I see it's an exponential function, or at the very least, the exponential function features in there. But because of the square, I really am not sure what to expect. I'm used to thinking that I don't have symmetry, but the square's presence might change things, and it's okay to not really know. I might have some horizontal asymptotes, I could say, but until I get to those steps, I really don't know for sure. Y-intercept I can do. Plug in 0, I get e to the 0, which is 1. So that was pretty straightforward, to the point where we can go and put it on our graph. Feel good about the graph, get something going, why not? Let's see what we can do here. No, not a square, that one. Let's put something on the graph. Build some confidence, get some momentum. There it is. 1. I got something. Next up, asymptotes. Asymptotic behavior. Where I want to see, are there any asymptotes? What is happening? Alright, so I want to know if x is going to infinity, what is happening to my function? Well, a good rule of thumb is whenever I see a negative in the exponent, I can rewrite it. And that reminds me, ooh, there's a denominator happening, and that might allow me to do certain things and just see it in the right way. So now, if I look at the form of this limit, we look at just how the numerator is behaving. 1, doesn't change. Just how the denominator is behaving. And with a positive exponent, it makes it a little easier. So I know it's e to the something. If that's something, how does that something behave? Well, if x gets really big positive, x squared gets really big positive, so e to the something gets really big and positive. And therefore, the limit is 0. On the other hand, I have to also look at the limit as x goes to negative infinity of this function. Form of the limit gives me an indication of how the pieces interact. It's going to be 1 stays 1. Now it's e to the something. As x gets big negative, x squared gets big positive. So I have e to the something, where the something gets big positive. So I have another 0. So we'll write it over here. I have a horizontal asymptote on both sides, the line y equal to 0. Do I have any vertical asymptotes? That can only happen with the exception of a log function being present, where the denominator equals 0, but e to the something is never going to equal 0, so there are none. So let's put it on my graph. I have a horizontal asymptote, and I'm not sure how I'm approaching it. Leave it open because I know the next step is going to show it automatically. There's no need to worry about that here. So we made some progress. Step 3, we want to look at increasing and decreasing behavior. And for that, we need to look at the function, its derivative. But I want to look at the function in the most convenient form. I'm not going to look at this guy and do a quotient rule, especially not coming out of my previous rational function. I'm kind of done with quotient rules unless I really have to. I'm going to look at this version, because taking the derivative of an exponential function with a chain rule is not so bad. So, looking for the derivative, it's e to the something. So the derivative is e to the something times the derivative of that something. And then I can clean it up and put the negative 2x in front maybe. That looks kind of nice. Like so. Now again, I see I have a negative exponent, so it might be useful for what's coming up to see it in its fraction form. Not necessary, but it's helpful sometimes. Then my 2 checks require that I look at when the derivative is equal to 0, when the derivative is undefined. When is it equal to 0? When the numerator equals 0 and therefore x equals 0. When is it undefined? It's going to have to be when the denominator equals 0, but because it's e to the something, that is never going to happen, because that's never equal to 0. So I have one contender. Let me just clean up my equal sign here. There we go. One contender to be a critical point. I'll make my table. Now, you could actually decide at this stage, is this a critical point? Do I have a y value corresponding to x equal to 0? Yes, I do. It was the x-intercept. It's 0. So that is immediately a critical point. It's in the case of inflection points where I need to check the table and the concavity has to actually change. In the case of critical points, it doesn't matter. If it comes out of this and there is a point, it's a critical point. Now I have some pieces. I can make my table, but my table is only split at x equal to 0. I have a negative 2x. I have an e to the x squared. Together they give me the first derivative. Split it up over here. 2x is 0 when x is 0. It's in the numerator. Makes the whole function 0. E to the x squared is never 0. In fact, it's always positive, because I know what the shape looks like of e to the something. Negative 2x is going to go positive to negative. Now, by way of multiplication and division, two positives will make it positive. Negative and a positive will be negative. So I have an increasing section, 0, whoops, let's make it nice and horizontal, 0, negative. So I see my little crest shape. Let's finish it by writing our sentences, maybe over here. F is increasing on negative infinity to 0. Should I include the 0? Yes. Function's defined at 0. F is decreasing on 0 to infinity, including 0. So what can we put in our graph? Well, this tells me what arrows are happening. Can't be this guy, because I am increasing. Where's turn off my eraser? There we go. I have a little cup here, and then I'm decreasing. So it can't be that bottom guy, because I'm not turning again. Now, we have found what the first derivative tells us. Let's see what the second derivative tells us in the concavity. So for the second derivative, I want to look at the easiest first derivative. And I like to look at this guy. I am a little tired of the quotient rule. If I can avoid it, maybe that's not a bad way to go. So I'm going to see my first and my second in the product rule. So now let's just move up and down a little so we don't make a mistake. Derivative of the first is negative 2. I don't know if you can hear, someone is walking upstairs. I apologize if it is noisy on the video. Derivative of the first, negative 2, times the second, e to the negative x squared, plus the first, which is negative 2x, times the derivative of the second, which is e to the something, times the derivative of the something. So it requires a little bit of cleanup here. I can do it in multiple steps, or I can say, well, this guy is in both, so let's take it out as a common factor and see what I have left. I have left a negative 2. And if I put these together, it's a negative 2x and another negative 2x, so there'll be a plus 4x squared. Plus 4x squared. So now let's just see what is the simplest way to look at that and to write that. Before moving on, I definitely want to move this down. You can take out a 2 if you want to. Sure, why not? And maybe have 2x squared minus 1. Let's just check. Multiply it back in, I get 4x squared. Multiply it back in, I get negative 2. So that's good. And maybe move this guy to the bottom. That's maybe my best option for looking at the second derivative. I then have my 2 checks. When is the second derivative equal to 0? Well, it's going to be when 2x squared minus 1 is equal to 0. So that means x squared is equal to a half. So that means x is equal to plus or minus 1 over root 2. Oh, my bracket is way too short, isn't it? Next, when is the second derivative undefined? When the denominator is 0, but that's not happening because it's e to the something. So that's a never. Whoops, that was only supposed to be never. Whee, like that. So I have my possible inflection points at plus minus 1 over root 2. Not ideal, but it is what it is. Can I squeeze in my table? I'm going to squeeze in everything over here. Why not? I think I can. Now it's split up my x-axis into negative 1 over root 2 and positive 1 over root 2. Ooh, that was not good. You can go decimal if you want to, but the root 2 is pretty clean number. So, I have my pieces. Write the 2 if you want to write the 2, because sometimes it's negative and it plays an important role. 2x squared minus 1 and e to the x squared. The only way to get better at these really is to just see a little variety in the functions, and you get used to them. Used to watch out for, used to where the possible mistakes can be. 2 is always positive. I'm going to do the exponential one next. Each dx is always positive. Oh, that's also very nice. Now, you could factor 2x squared minus 1, but most people, they could make a mistake, so I want to show you don't have to. But I had 2 zeros coming out of that guy. So 0 whenever I have negative 1 over root 2 and positive 1 over root 2. They are in the numerator, so it makes the second derivative 0. Plug in representative numbers, see what you get. It's going to be positive, negative, and positive. It can only change over the zeros, but depending on how simple or not simple your piece, your factor, your expression is, it could change multiple times. So, no negatives in the first section, 1 negative, no negatives. Concave up, down, up. Let's write them down. F is concave up on negative infinity to negative 1 over root 2. Should I include 1 over root 2? Yes, I should. We're going to calculate those values in a second. 1 over root 2 to positive infinity. Squeeze it in. F is concave down on negative 1 over root 2 to positive 1 over root 2. So we just want to find what are the y values in each case. Now you could go decimal. Remember my function? Where's my function? Function up here somewhere. Function up here. So if x is, well, I can see the function. Let's just do it this way. instead of scrolling up and down. If x is negative 1 over root 2, then y is 1 over e to the square of this, which is 1/2. Or 1 over root e. You can calculate that on your calculator if you want to, or not. And it's also going to be the case when x is negative 1 over root 2, because I'm squaring it there. So I get 1 over root e. 1 over root e. 1 over root e. Now let's take our calculators and calculate. What is 1 over root e? I'm curious. I want to know. So 1 divided by square root of... Oh dear, where's e on my calculator? How do I not have e on my calculator? I don't see e on my calculator. I'm just using no, I don't have it. I'm just using a temporary calculator. Okay, hold on, I can do it. 1 divided by square root of e. Go. 0.6065. 0.6065 if I round to 4 decimal places. Alright. So, do I have an inflection point here? Yes, they're points. They come out of my check. The concavity changes, so they are inflection points. Or there are inflection points at these x values. Let's see where this sits. So it's 0.6, right? So it's, let's suppose it sits over here and here. So this is 1 over root 2. This is negative 1 over root 2. And this is 1 over root e. Now I'm bending. How am I bending? Up, down, through the 2 points. Down through the 2 points. That makes sense. Up, up. Okay, so it does make sense. Let's make a nice clean graph. And it's because of the x squared that I don't have the basic e to the x shape that I'm used to. I have 1 here. I'm going to go down, bending, and it's going to change, maybe not right there, maybe over here, at negative 1 over root 2, 1 over root e, and then I'm going to go down, whoopsie, down, come on, and bending up to my asymptote, there, at 1 over root 2. And there we go. That is the graph of e to the negative x squared. Alright, the next one we're going to do is number, where is it? I just saw it. 34. X times log of x. Let's call it f. X times natural log of x. So of course we're not doing absolute values here, as you might see, so this is only defined for positive values of x because of the log component. So I see that there is a logarithmic function, I'll call it a log component, which means the function's not going to be defined everywhere. I could have vertical asymptotes. We will have to see. Can I find a y-intercept? Well, for that I need to plug in x equal to 0. And that is not gonna go well. So none. Alright. So we go ahead and see if we have any asymptotes. Asymptotic behavior, rather, which is just a fancy word for find some asymptotes. So I look at my function, and I see, well, what happens? I have to ask, in general, what happens when x gets really big, positive, and negative, but in this case, there is no negative side to speak of. So, x times natural log of x. Now, what is the form of this limit? The form of the limit is, well, x goes to infinity, and log of x, I remember the shape, also goes to infinity. A little slower, but still. So I have two large positive numbers, so large and positive. So some of these limits are, or can be, quite straightforward. And so I have no horizontal asymptotes. It makes no sense to look at the left side. There's nothing there. What about vertical asymptotes? Well, I know that for the log function on its own, I have a vertical asymptote at x equal to 0. But the presence of this x might change things a little bit. So I want to check if x gets close to 0 from the right, what is happening to the function? Does it still go to infinity, plus or minus? This is a little bit more complicated than just checking in a rational function for a 0 denominator. What is the form of this limit? Well, x goes to 0, and log of x goes to infinity. Now, this isn't a number, so it's really a question of how fast these go. If the first part goes to 0 super fast, relatively speaking, it can control the whole change in the function, and the whole thing can go to 0. But if the second part grows fast before the first part can shrink, the whole thing can blow up. So very similar to 0 over 0 or infinity over infinity, anything can happen. So what I want to do is I want to rewrite this so that it looks like a fraction. So I'm going to put the log of x over 1 over x. Then division by a fraction is multiplication by the reciprocal, and I get my original function again. So I'm just going to do it up here. What is the form of this limit? Now the log function goes to negative infinity as x gets close to 0. And the bottom 1 over x also goes to infinity when x gets close to 0. I don't care about the plus or minus. If it's infinity over infinity, I can use L'Hopital's rule to see how does this thing really behave, to be absolutely sure. Now, the derivative of log of x is 1 over x. The derivative of 1 over x, remember this is negative x, not negative x, I'm doing the derivative, x to the negative 1, which has as derivative negative x to the negative 2, like so. If I now simplify this a little bit, and I cancel the x's, or this goes up at the top and get multiplied by x squared over 1, negative of course, then I see this simplifies to negative x. And as x gets close to 0, this gets close to 0. Yeah, from the left, but I don't really care that much, to be honest. But sure, you can indicate it from the left. What does that mean in terms of my vertical asymptote question? No vertical asymptote. I have to get an infinity or plus or minus. there are no vertical asymptotes. So yes, the presence of the log function does make things a little bit more complicated. Just remember that 0 times infinity is also a little bit of a problem where I can't be sure what happens. It depends on the pieces. So this being 0 actually means that x goes to 0 faster than log of x goes to infinity. So it can dominate and control and shrink the whole thing. So as a result, I can not put anything on my graph. I can make a graph, but I don't have a Y-intercept. I don't have asymptotes. I kind of have nothing at this point. Not the start I wanted, I was hoping for, but there it is. Nothing. Maybe step 3 will shed some light on this, where I'm looking for increasing or decreasing behavior. There I'm going to look for the derivative, and my original function, remember, is quite straightforward. I'm going to use the product rule, derivative of the first times the second plus the first times the derivative of the second. Let's clean this up a little bit. I'm just going to write this, which simplifies to 1, at the front, so I don't get confused. If I write log of x plus 1, I get confused. Is it this? Is it this? What's inside the log? So to avoid confusion, I just reorder them, and I never read this incorrectly. So there's my derivative. Super easy. Now I still check backwards, like this. When is this derivative equal to 0? Well, I'm gonna be able to find that by setting it equal to 0. That means that log of x equals -1. And if I rewrite this to the exponential version of the equation, I get e to the -1 equals x. So in other words, x equals 1 over e. Alright, now we have something, and oh, my little curly bracket here was a little premature. The other check I do have to make is when is the derivative undefined. In addition, of course, to the basic domain where the valid x values are. Outside of that, I'll say here, no additional x values. There's nothing extra that I'm getting out of this. I know there's a log component, so having anything 0 or negative makes no sense. So I will make my table over here, and I'm only splitting it at 1 over e. I have one piece, and it gives me my derivative. This piece, 1 plus log of x, is 0. We've established when x is 1 over e, it is the derivative, so it makes it 0. Now you can plug in little representative numbers here. You can't plug in 0, but 1 over e, let's see what is 1 over e in case you are curious. 1 divided by e is 0.36-ish. 0.3679. So plug in a 0.1, plug in a 0.5, see what you get. You'll get a negative and a positive, which is then the same for the derivative. Then I have a negative slope, I have a horizontal, and I have a positive. So it shows the cup shape that is happening. We can write our sentences. F is increasing on 1 over e to infinity. Should I include 1 over e? Do I have a y value when I plug in 1 over e? Yes, I definitely do. and f is decreasing on negative infinity to 1 over e. Don't do this out of habit. There is no left side here, remember. We should maybe clarify that by saying here undefined when x is negative or less than or equal to 0 because of this log component. So as a reminder, it might be beneficial to put a little 0 here and say bad things are happening undefined. So then when you see it there, it reminds you, oh, I can't do this. It can only start at 0. And I can't include 0 either because of the log. So maybe that helps a little bit. Is this a critical point? Yes, it is. Because it comes out of my check and there's a point. There is a function value. So finally I have something to put in my graph. I have something interesting happening at 0 in that there's only a graph past that. I am finding something at 1 over e, and that something is, did we find a y value? We did not. We probably should. So let's say up here, if x is 1 over e, then y is f of that, and my function is x times log of x. So 1 over e times log of 1 over e. That's going to, well, this guy is negative 1, so it's negative 1 over e. So negative point, what did we say, 3679. So that's going to sit down here, negative 1 over e. And I know it's coming down. Let's just do the right side first. I know I'm going up to infinity because we found that over here. But what happens when I get close to 0? I'm going to head to 0 from the left, from below negative numbers. So I'm going to head towards 0 like this. But if I go left to right, that confirms I am decreasing. Sorry, this negative is very close here. I'm decreasing, turning my little cup. Let's do the little cup. There we go. And then increasing. So the shape is sort of starting to take shape. We just need confirmation from our concavity step. I'm just going to make a new page to make sure I can fit that in. So concavity times step 4, concavity. I'm looking to find the second derivative, and I'm going to pick the most convenient, best looking first derivative, which is going to be this guy, obviously. It's very simple, it's just 1 over x, based on this. That's super nice, wow. I barely need a table, but I'll do it anyway. Can I write my bracket the right way around? That would just be lovely. Like so. Oh, it was right, huh? Second derivative is 0. Never. Numerator is 1. Second derivative is undefined when x is 0. Now this function, it's interesting. This function, this second derivative function, doesn't know where it comes from. It happens to come from this function in 2 steps. It doesn't know that it shouldn't be defined everywhere. It just does the thing. Hey, do with me whatever you want. I have a problem at 0. I don't really care about the rest. So I'll make my table. So you have to see it in the context of what the original function wants. on its own, the second derivative doesn't know where it's coming from. It's saying, here's the information as far as I know. Do whatever you want with that. And we have to compare it back to our original function. So these are the pieces. Splitting it up. 1 is always positive. The next piece, x, is 0 when x is 0. In the denominator, second derivative is undefined. It's going to go negative to positive. The second derivative is negative to positive. It's very simple. Now it looks here, oh, I'm bending down, I'm bending up. Yes, but remember, there are no valid x values here. So even though the second derivative says, hey, if you're interested, I'm bending down, if it makes any sense, it doesn't make any sense because of where it comes from. So we'll say f is concave up on 0 to infinity. Do I include 0? No. It's not defined at 0. Is this an inflection point? No, for multiple reasons. It's not a point. And my concavity isn't changing as I pass through that point either because there's nothing on the left. So not much is happening. But it does say it's bending up wherever I am, which is over here, bending up throughout. So that's all the information that we have. Now let's graph it. I'm just going to make a new graph so it's as neat as possible. I know I don't really need the left side here because there's nothing there. So at 0 something's happening, 1 over e, negative 1 over e. I still have a nice critical point. Did we label that as a critical point? Yes, we did. Okay, good. Oops, this one. So I have my shape here. Let's go from the turning point up. Oh, that was very wobbly. I officially apologize. There we go. Unofficially, I have to do it in these sections, otherwise my line isn't very smooth. So squint when you look at it. So there's my critical point over there. I just want to check. So I'm heading towards this 0 in a bending up manner. How should I approach it? I know it's not actually there. It's open. Like I can't be at 0. Do I approach it as an angle? Do I approach it at a somewhat vertical tangent line or a tangent line that wants to be vertical? Let's have a look. So let's write it on here actually. There. F of the derivative is approaching what as x approaches 0 from the right? That'll tell me how the slope behaves. So I'm looking at the derivative here. As x approaches 0 from the right, what does this mean? How does this behave? Well, 1 plus log of x is simply a vertical shift of the log function up by 1. So that means that as I'm approaching 0, so that's an extremely ugly graph. That was much better. As I'm approaching 0 from the right, I'm still going to negative infinity. Negative meaning I have a negative slope, which makes sense. Here it's all negative. It's all decreasing. But I am heading towards a vertical slope line. So I need to meet this as vertical as I can while starting from horizontal, like so. But I put a circle, open circle around there, showing that I never actually get there. So that is my graph of x times log of x, which might not quite be what you expect. Alright, the last question we're going to do is number 40. which is my function. Let's call it f, x to the 5 over 3 minus 5x to the 2/3. So I'll call this function type fraction powers of x. So aside from the fraction aspect, it looks very polynomial-like, but we'll see it makes a big difference. I can, however, say what the y-intercept is. When I plug in x equal to 0, I get y equal to 0. Now, by identifying what the function type is, I do recognize that, when I get to asymptotic behavior, it actually has a lot of similarities with polynomials, in that for these positive powers of x, I have to answer the question if x goes to infinity, approaches infinity, then my function is going to behave like its leading term. I say that when I have all positive powers of x, of course. Now its leading term is this guy, so that's the only one I need to look at. Now remember, I can rewrite this as x to the power of 5, the cube root, minus 5 times x squared, the cube root. Maybe that cube is not very clear. There we go. So, x to the 5 gets bigger when x gets bigger, positive. Cube root of a big positive number, big positive. But if x that was supposed to be an arrow. When x approaches negative infinity, then it still behaves like its leading term, a large negative number, and x to the 5 will also be large negative. Cube root of a large negative number, large negative. Regardless, I have no horizontal asymptote. I also have no vertical asymptote. Because of the cube root and the positive powers, it's defined. F is defined for all x values. So there can't be any vertical asymptotes. So I do have some information. Let's start a graph and feel good about putting stuff on it. Let's make our axes over here. We have a y-intercept, and we said it's going up to the far right, and far left it's going to go down. Alright, that's something. Next, we want to see where is the function increasing and where is it decreasing, and how does it behave? For that, we need to find the derivative. Now, that's not a very complicated derivative to find, just the power rule based properties. So it's 5 over 3 x to the 2/3 minus, let's leave the 5 out. 2/3 go in front, x to the negative 1/3. Now, I have to clean this up. So, these two together become 10. I can take out a 5 over 3. And let's just do that first. I'm left with x to the 2/3 minus 2x to the negative 1/3. Don't try and do too much at once if you're not comfortable with it. Now a good rule of thumb here is to take out the smallest or most negative power of x, which in this case is going to be x to the negative 1/3. Then I'm left with x minus 2. And it just makes that bracket as nice as possible. If I clean this up, I get 5 over 3, x minus 2, all over x to the 1/3. Now, we want to see, I'll do it up here. When is the derivative equal to 0? And that's the benefit of writing it in this simple, nice form. I can just see it's x equal to 2. When is the derivative undefined? I can just see it's x equal to 0. So having done some cleanup work, I now reap the benefits. So I have two potential critical points. Let's make a table and see how they interact. Whether it's an actual critical point or not, it goes in my table. They're equally important for me in where the function could change from bending up to bending down. So I list all my pieces here. X to the 1/3 is another piece. Together, they give me the first derivative. And I have these sections that I need to identify. Is the derivative positive or negative? Well, 5 over 3 is always positive. X minus 2 is 0 when x is 2. It's in the numerator. Here's my derivative. It's in the numerator, so it'll make the derivative 0. It's going to go negative, negative to positive. X to the 1/3, or the cube root of x. That is an ugly root. Wow. Is going to be 0 when x is 0. It's in the denominator, so it makes the function undefined. It's going to go negative to positive as well. So I have two negatives, one negative, and no negatives. So if I now look at my slope lines, I'm going up, bad things are happening, down. I'm going down, horizontal tangent, up. So I have my cup shape here, but who knows what's happening there on the first one. Regardless, I can write my sentences. I'll do it over here. F is increasing on negative infinity to 0. Should I include 0? Yes, I should, because this is referring to the original function. Original function is perfectly happy with 0. Also on 2 to infinity. Should I include 2? Yes, I should. F is decreasing on 0 to 2. Include them both, because the function is defined everywhere. Just because the derivative is undefined doesn't mean anything. For this sentence, I'm looking at the function. Are these critical points? Critical points. The requirement is critical comes out of this derivative check. Points, function has to be defined there. So yes, they are. 0, 0, we've already found was our Y-intercept, right? So here, y equals 0. When x is equal to 2, what is y equal to? Well, I go up, 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 and I plug it in. Use whichever version you want. I like the root version for calculations. When x is equal to 2, so let's go slow and do it. cube root. I need to look, where are my cube roots? Cube root of 2 to the 5th power, which is 32, minus 5 times cube root of x squared, which is 2 squared, which is 4. Negative 4.7622. Negative 4.7622. So let's put these critical points on a graph. 0, 0. And what happens there? I don't really know right now. And 2, negative 4 point, what did we say? 7622. Lost my mouse. There it is. 7622. Right there, I'm going to have a little cup. Here, I'm not sure. Well, I mean, I am, but at this stage you might not be sure. I am, however, going to be increasing up to the 0 point, decreasing down, and then up again. I think we should maybe try and figure out what's happening at 0. Well, I know my function's defined there. I have a point, I have a critical point, everything is okay. But when I look at the tangent line, slopes, in other words, the derivative, it's undefined. What happens to this function, this derivative function, when x gets close to 0? The numerator isn't getting close to 0. It's getting close to like negative 10 over 3. The denominator only is shrinking down, and the result is the whole thing is going to blow up. So I'm going to have a vertical tangent line. Vertical tangent line at x equal to 0. So I'm going to write a little thick line there to remind me. Alright, next up is how the graph bends. Ooh, I think we can do it. So we'll do step 4, which is concavity. For that I need the second derivative, but this is easier than you might think. I'm not going to look at this version. I'm not going to look at this version. I'm going to look at the original. But maybe we should clean it up a little bit. So let's just write it over here. What was it? 5 over 3 x to the 2/3 minus 10 over 3 x to the negative 1/3. That is the nicest version to calculate the second derivative from. Might not be the nicest version to use in step 3, but it is now. So I have 10 over 9 x to the negative 1/3 plus 10 over 9 x to the negative 4 over 3. Now I need to clean this up, of course. I'll take out a 10 over 9. And I'm going to take out the smallest, or most negative, rather, power of x, which is negative 4 over 3. What do I have left? I have, actually, x plus 1. And by doing that, I have a nice bracket here, easy to work with. So I have 10 over 9, x plus 1, x to the 4 over 3 in the denominator as my second derivative. So these ones are actually not bad at all. So I look at where my second derivative is equal to 0. Having done the work to simplify, it's as easy as saying x equal to negative 1. Where is the second derivative undefined? Having done the work, it's when x is equal to 0. So I almost have space for my table. I'm going to squeeze the table in here. I think we can do it. There are only a couple of pieces here. I'm going to separate it by -1 and 0. Together, these pieces give me the second derivative. I think we can fit everything in. Now, 10 over 9 is always positive, positive, positive. X plus 1 is 0 when x is -1. It's going to go negative to positive. X to the 4 over 3 or x to the 4 cube root is 0 when x is 0. Sorry, we didn't say. X plus 1 is 0 when x is -1. It is in the numerator. It makes the function 0. X to the 4 over 3, or whatever version you want to look at, is 0 when x is 0. It's in the denominator, undefined. I work inside out, which is why I want to look at the root version instead. X to the 4 is always positive. Cube root of a positive number, positive. So I have on the first section, negative, positive, positive. So I'm bending down, then up, then up. Let's write these sentences. First, f is concave up on, can I say -1 to infinity? Yes, I can, because I'm referring to the function, which is defined everywhere. F is concave down on -infinity to -1. Next question. Are these guys inflection points? Which one is an inflection point? They're both points. They're contenders because they came out of my check here. But the concavity has to change as I pass over these zeros. It does for -1. It doesn't for 0. So only this guy is an inflection point. They're equally important in my table, but an inflection point is only one where the concavity changes. Now let's see what we get here. Alright, graph time. I'm bending down -1 and to the left. Whoa. -1 is sitting somewhere over here. But what is the y value? I said there's a point. What is the y value when x is -1? So let's go all the way up. X is now -1. And calculate what is the y value. So I have the cube root of -1 to the 5th, which is going to be -1, minus 5 times the cube root of -1 squared, which is 1, and I get -6. -6. So, way down here is -6. I'm going to bend down to the left. So I'm going to bend this way as I'm heading to infinity. Not a big bend. Then I'm going to bend up through here, of course. I can see that bend clearly. But also here, I'm going to bend up. So let's finish the graph in a somewhat neat way. And then we have covered all our types of functions. So we have our vertical tangent line here. Let's just take care of the other side, the right side. Let's put it over here. Horizontal tangent up, up, and away. And then I'm going to go vertical tangent towards this horizontal cup. Now I know this is sitting here at negative 4.7622. And I'm going to go vertical tangent, bending up. I'm just going to exaggerate this a little bit so you can see. Come on, not straight. So you can see the bending occurring here at negative 6. Up x equals negative 1. And then I bend down, not straight. It looks very straight. Whoop, that was a wobble. Down to infinity. So I get these very interesting shapes in my graphs when I allow for fraction powers of x. But all the information still comes from my previous steps and my tables, like before. Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.